Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And welcome to our group video presentation. Today we will discuss about drug concentration in a two-compartment system. Before we dive deeper into the topic at hand, we will take a look at a more general topic that has a connection to our subject matter, which is pharmacokinetics. We divide the word into two Greek terms, which is pharmakon, meaning drugs, and kinetikon, which is putting in motion. From these two terms, we could say that pharmacokinetic is a study of how the body interacts with administered substances or drugs for the entire duration of exposure. To simplify, pharmacokinetics is a study of the drug flow in the bloodstream. Now, we will touch back to our main topic. The purpose of this mathematical model is to investigate the pharmacokinetic rate of drug distribution from one tissue to another through the human body. We will look at what are the two compartments that are mentioned in the model. How will it compare to a one compartment model? Throughout this video, we will explain how the equation is obtained and how to solve it. So these are our study objectives for this topic. It is first to draw the scheme and write the differential equations appropriate to a two-compartment pharmacokinetic model. Next is to recognize and use the integrated equations for these models to calculate parameter values and for dosage regimen calculations. And finally is to calculate the parameters of these models using the method of residuals.
Alright, now we will see the explanation of pharmacokinetic model, and firstly we need to see the side-by-side comparison model between one compartment model and multi-compartment model, and in our case we have two compartment model. Okay, so as you can see, in one compartment model, the graph only consists of a straight line, whereas the two compartment model, they have a little bit of curving which represents the fast phase and the slow phase. Why is this happening? In slow phase, the drugs needs to cross over to the cell membranes to stick to the tissues and the organs in the human body. Okay, so now let's see more details in two compartment model. So as you can see in the diagram up here, we have three compartment in two compartment model. The first one is X1, representing the central compartment. The second one is X2, representing peripheral compartment. And peripheral compartment usually consists of tissues or organ in human body. And lastly, X3, which is the elimination compartment, usually consisting of kidney or liver. Okay, so for the parameter of movements of drug from X1 to X2, we represent them as K12. And the vice versa movement, we represent them as K21. And last but not least, the movement of X1 to X3, we represent them as KEL. So by that, we get our two ordinary differential equation. The first one is dx1 dt, which is equals to minus KEL x1 minus K12x1 plus K21x2. The second ODE is dx2 dt, which is equals to K12x1 minus K21x2. And by these two differential equation, it means that our pharmacokinetic model consists of matrix system. And by this, we have our suggested solution, which is Cp equals to A times e to the minus alpha t plus B times e to the minus beta t.
Okay, now that we have our system of differential equations, we can actually represent this in a more compact form with vector matrix product, which we can represent it as x prime of t equals to a times x of t, where a is the coefficient matrix with entries negative kel minus k12, k21, k12, and negative k21. Okay, and so how do we know if this system actually has a solution? Well, it's given by this theorem from the Nagel, Seff, and Snyder textbook, Fundamentals of Differential Equations, and it states that if a of t and f of t are continuous on an open interval I that contains the point t naught, then for any choice of the initial vector x naught, there exists a unique solution x of t on the whole interval I to the initial value problem x prime of t equals to a of t times x of t plus f of t. And so in our case, our interval is the interval 0 to infinity, and clearly our a, which is the matrix, our a in this case is continuous in the whole interval because it is just numbers, and f of t for our case is 0 because this is a homogeneous system of differential equations, and so that means it is continuous on the whole interval. Therefore, by this theorem, we do indeed have a solution given an initial vector x naught at t equals to 0. To solve this system of differential equations, we will use these example values for the parameters. So in the end, we will get this coefficient matrix A as well as this initial condition. To solve this system of differential equations manually, we will use the method of finding the eigenvalues and eigenvectors. So we will get the equations for the amount of drugs in each compartment. Then we divide both equations by the volume of compartment 1 to get the equation for the concentration of drugs in each compartment, which is shown here in the highlighted box. Next, for the computer-aided solution, we will use Python's SymPy library to solve this system of differential equations. The code is shown here in this slide, and the solution is exactly the same as in the manual solution. This is because it is proven from the theorem we saw earlier that stated that this equation has a unique solution. Next, we will plot the graph of the two equations, and we see the plot for C1 is exactly the same as the plot we had seen earlier. And the plot for C2 is the expected outcome, which is an initial 0 concentration to a certain peak before decaying to 0.
Okay, for the conclusion, the result presented above is the solution that we get from the computational and manual solution. We must note that the numerical values are only approximation of the exact values to simplify the presentation of the model. Okay, for the recommendation on how we can improve the model, firstly, incorporating more compartments that represent different organs or tissues in the body can provide a more detailed and accurate representation of drug distribution and elimination. This can help to better understand how a drug is distributed throughout the body and how it is eliminated over time. Another important recommendation is to incorporate nonlinear pharmacokinetics in the model. Many drugs exhibit nonlinear pharmacokinetics where the relationship between dose and concentration is not linear. Incorporating nonlinear pharmacokinetics models can provide a more accurate representation of drug disposition and help to better understand how a drug is metabolized and eliminated by the body. Additionally, incorporating physiological-based pharmacokinetics or PBPK model can also provide a more realistic representation of drug disposition. PBPK models take into account the physiological factor that can affect drug disposition such as blood flow, organ volume, and membrane permeability. This can help to better understand how a drug is distributed throughout the body and how it is eliminated over time. And finally, validate the model by comparing the predicted drug concentration with the observed drug concentration in human and or animal studies. This can help to ensure that the model is accurate and reliable, and that the predictions made by the model are consistent with real-world observation. Okay, I believe that sums up our presentation. Thank you all and thank you, Doctor, for listening. We hope you found the information presented valuable and informative. If you have any further questions or would like to discuss the topic further, please don't hesitate to reach out and have a nice day.